So we now move on to a new topic, and this is before the application part. This is the final topic of mass transport phenomena, and this is mass transfer, convective mass transfer, and it is divided into two segments. One is convective mass transfer between a solid and a fluid. That's what we are going to discuss today, and in the next lecture we'll talk on convective mass transfer between two fluids. These are all very relevant in our kinds of processes. For example, solid and liquid mass transfer arise frequently. For example, you can see gas-solid reactions are very common. You have an iron ore pellet and a hydrogen gas or a carbon monoxide gas is passing. So what is happening is oxygen from the ore is getting transferred into the gas phase, which is in turn carbon monoxide becoming CO2 or H2 becoming H2O. So this is the gas liquid, this is the gas solid mass transfer. We also have solid liquid mass transfer. For example, we make alloy steels, for example, or we alloy a metal, and what happens is we typically add solid materials and then the alloying elements dissolves. So the alloy which is present into the solid state now goes into the dissolved state. So that's a solid liquid mass transfer. And also we have two fluid mass transfers, which is very common in the context of slag metal mass transfer and so on and so forth. So this needs to be covered, and as we will see that when you address solid liquid or solid fluid mass transfer or liquid liquid mass transfer, diffusion is important, but superimposed on diffusion there is the role of convection which aids in the mass transfer process, and that's what we are going to discuss today. Now, I have discussed some fundamentals with regard to heat transfer between a solid and a fluid. We have not talked about heat transfer between two fluids, okay? But mass transfer between two fluids is a very important topic because there are slag metal reactions, gas liquid reactions, gas solid reactions, and so on and so forth. So we will address the phenomena of mass transfer between a solid and a liquid a little bit more detail. And the first thing to ask is or to discuss is that we have the solid, and this is the fluid phase, and this represents the interface, okay? And there is a interface here. So this part we have already addressed, that if this represents if this is the solid and this is the interface, so within this the mechanism is mass transport is diffusion, and that we have covered extensively, nothing needs to be said. We now want to look at to the right of the interface, that's into the fluid phase, that what really happens, and there we have flow is taking place, and as a result of which the solid may be getting transferred into the fluid. We'll discuss the applications, but this process you can show an example, for example, with respect to leaching. Okay, leaching, as you all know, that you take bauxite, you take sodium hydroxide, you have studied that, and you get a leach solution which has all the alumina from bauxites get into the leached liquor, and it becomes sodium aluminate. So that is a solid liquid mass transfer in the Bayer's process, for example. And so therefore the solid is there, the fluid is flowing past the solid, and as a result of which what happens, the species which is present into the solid has a dissolution, progressively dissolves into the liquid. Similarly, if you are adding carbon into iron to make it or steel to make it high carbon steel, or maybe pig iron, in that case what happens, the carbon may be in the solid phase, and then the liquid steel will flow past carbon, and as a result of which carbon will progressively get dissolved into the fluid. So we want to now look at the rate of mass transfer, the mass transfer mechanism, how we can calculate, how we can distribute the find out the concentration, and so on and so forth in the fluid phase. So our domain of interest is now from the interface to my right, and that's what is the fluid phase. Now if you look at this we have explained, so this is the corresponding, and if you now draw the distance, so this is my, say, x is equal to 0, that represents my interface, and that is my x is equal to 0. So this is my distance from the interface, and this is my velocity. So there's the velocity of the fluid, and this we all know that we have the velocity approaches something like this. The velocity is 0 here at the solid wall because this is solid. So it is 0, and then the velocity increases, establishing a characteristic boundary layer, which I have already told you. And we have seen that the boundary layer itself can be divided into several parts, and most important thing is that you have a laminar sublayer here, then you have a transition sublayer here, and then we have the bulk of the fluid. Now, where the flow in the industry is mostly turbulent in nature because the reactor size is large, and the fluid that we often talk about, having smaller kinematic viscosity, which makes Reynolds number typically very large. So this is a laminar sublayer. So, and this is maybe a transition layer, and then transition sublayer, and then laminar sublayer, and then the bulk. Now, the generalized expression, so if we similarly, if you look at the concentration profile, for example, and concentration, we know that from the interface there is a, because it is dissolving here, and as a result of which there is a driving force for concentration, the surface concentration minus the bulk concentration, that represents the driving force. So the material gets progressively dissolved into the fluid phase. If the fluid phase, to start with, has a concentration of the dissolving species which is equal to the saturation concentration at the solubility limit, then obviously there is no mass transfer from the solid to the liquid, because already the maximum concentration has been reached. Okay? But given that the fluid, the far field concentration, if it is C0, if this represents the far field concentration, and if we say that the solubility limit of the solid is Cs star, then obviously the mass transfer takes place, because the bulk concentration, sometimes it is also said that it is C sub B. Okay? So I will say, here I will write in that case. So this is either the bulk concentration. They are the one and the same thing. The free stream, it is synonymous to the free stream velocity. So the free stream velocity is u infinity, and the concentration is C0 or Cb, and as it approaches, progressive dissolution of the solid takes place, because the saturation concentration and this surface concentration, as I have told you several times, is determined on the basis of assumption of an equilibrium, and in this case the reaction is that if I represents the species which is in the solid state, then I goes into the dissolved state. That is the reaction that is taking place in the interface, and this reaction is in equilibrium, assumed to be in equilibrium very fast, and as a result of that assumption we should be able to find out that what is the surface concentration. So if you now draw the concentration, so you have seen the velocity, now you see we also want to plot concentration along this particular axis, and then the concentration profile will, from a region of higher concentration, then we will have going to a lower concentration. That's how the concentration. So we have a concentration boundary layer also. Now, so this represents, this is what is my, that's what is my C0, or Cb, that's what I represents, and this is what is my Cs star, the surface concentration. So I would say C versus X profile and V versus X profile. That's what it. Now, what are the mechanisms of mass transfer? The mass transfer mechanisms are that we will have diffusion and convection. These I have already stated categorically in my first lecture. But convection we can split into two parts. One is the laminar convection, and the other could be turbulent convection. Turbulent mass transfer, I have also said in the context of particularly heat transfer, turbulent heat transfer is far more greater, the rate of turbulent heat transfer is far more greater than the laminar heat transfer, because of the simple fact that there are superimposed on the mean motion, there are eddying motions in the system. So, therefore, diffusion is there, diffusion, there is bulk or laminar convection, and there is turbulent convection. Anywhere you take in the fluid phase, mass transport from one region to another region, okay? The transport of mass from here to here, three mechanisms will be occurring. And as I said that somewhere turbulent convection could be, these are laminar convective mass transfer. I haven't written the full thing, turbulent convective convection or turbulent convective mass transport. So, somewhere turbulent convection will predominate, somewhere maybe diffusion will predominate. Particularly if you now look at the interface. So, the rate of mass transport will depend on the rate of diffusive mass transport, rate of laminar convective mass transport plus the rate of turbulent convective mass transport, and the flux is going to be responsible because of these three different mechanisms. And if you now concentrate on the surface, so I say that J is the flux, I want to evaluate that J flux is x is equal to 0. So, this is the surface flux at which the solid is dissolving into the liquid. Now, this therefore obviously will be the rate of diffusion at the interface, x is equal to 0, rate of convection or convective mass transfer at the interface plus the rate of turbulence. These three parallel mechanisms which are occurring simultaneously, taking the mass from here to here, are going to operate at the surface. But we note that at the surface, these are a function of the velocities. Okay? We know turbulence is going to be there only when the Reynolds number is large. For a given fluid, that means that the velocity has to be very, very intense. Laminar convection, okay, that will depend on whether we are here, and the laminar convection or the mean flow component is going to be 0 as we approach towards the wall. We have seen here that the velocity at the solid wall, as per our now slip boundary condition, becomes equal to 0. So, therefore, as we approach from the bulk to the wall, the contribution of the last term, turbulence, is going to decrease, okay, laminar is going to predominate, then the diffusion is going to predominate, and then ultimately laminar convection and turbulent convection will vanish the moment we reach this interface. So, therefore, at the interface, the flux is going to be exclusively dictated by diffusion. But that diffusion is, because this term at the surface is going to be 0, this term is going to be 0, and therefore, it is going to be diffusion which is going to be only. So, even on the fluid side, at the surface, okay, the mass transfer takes place by diffusion. So, this becomes equal to minus d dc over dx at x. This is a very important consideration here at x is equal to 0. D represents the diffusion coefficient. What does this indicate? If d is constant, dc over dx at x is equal to 0 represents the slope of the curve at x is equal to 0. Now, you can imagine that if I draw the slope of the curve here, the slope of the curve is continuously changing, and this is the slope of the curve. And we are talking of this slope of the curve, dc by dx at x is equal to 0. That is going to be. Now, you can imagine if the flow is very fast, then what is going to be this slope? This slope is going to be much more steeper, okay? Or the thickness of this region is going to be much more. So, and if the flow is very, very weak, in that case, the slope could be, this graph could be not so steep, this graph could be something like this. This is a low velocity profile characteristics. So, if the concentration versus distance takes, this kind of a profile, in that case, I would say that looking at the slope of the line, that this graph essentially represents the variation of concentration with distance in a fluid where the intensity of flow is relatively weak. So, the characteristics of the fluid flow will depend the slope of the line, and that slope of the line, therefore, even though it is diffusion, the information of convection is implicit in this, because we have c versus x to be evaluated at x is equal to 0, and dc dx at x is equal to 0, as I have indicated, and you can also visualize this, is going to be a function of the velocity. More is the velocity, lesser is going to be this particular distance on the x-axis, lesser is the velocity, more is going to be this particular distance. Now, if we look at this, okay, then this is an important distance here. If this distance is represented, this is not boundary layer. The boundary layer, as per our definition, you remember, where I said that if you take the concentration C, is there any concentration, and then you have Cs star, and then you have Cs star minus C0 or C bulk, when this ratio is roughly 99% of this ratio, in that case what happens is that we can say that point is to be equal to. So, if you say that at this particular point, this ratio by this ratio is almost is equal to 0.99, then I will say this distance is the concentration boundary layer. So, in terms of that, this delta which I have represented here is certainly not the concentration boundary layer, but it is a measure of the slope of the line. This is the slope of the line at x is equal to 0. This is what it is. And this distance is delta. So, therefore, I can say that the slope of this line is going to be delta divided by Cs, and this is Cb. So, the slope of the line I can approximate as minus delta, and dc over dx could be given in terms of Cs star minus Cb divided by delta. Because delta is a delta C is a term which we represent normally to represent the boundary. So, delta sub T is the thermal, capital T is the thermal boundary layer thickness, delta sub capital V is the velocity boundary layer thickness, and delta sub capital C is the concentration boundary layer thickness. But that it is not boundary layer thickness, but it gives us a good measure of the flux at the surface. This term is called the effective concentration boundary layer thickness, and it is denoted by delta sub C comma EFF. So, therefore, we can say that this term is going to be now, sign is going to be changed because I have written Cs minus, and therefore, we can say that Cs star minus Cb divided by delta C effective by D. This I have cast again in the form of driving force divided by the resistance. So, delta sub effective by capital D, or the diffusion coefficient, essentially represents thermal essential concentration resistance, concentration resistance, and we had seen that in the context of heat transfer, we have introduced the parameter R thermal. So, here in that case, this is going to be the parameter R sub C, the resistance due to concentration difference here. So, this parameter is given a name which we call as the inverse of this parameter, delta C effective divided by D inverse. Now, if this is a resistance term, obviously the inverse is going to be a conductance term, and this conductance term is known as the mass transfer coefficient. If you take it the units of this comes out to be meters per second. That's the so therefore, we can say it is equal to, typically small k is written k sub m into Cs star minus Cp. Note that this mass transfer coefficient is a function of the velocity. Why? Because this mass transfer coefficient is a function of effective concentration boundary layer thickness, and as I have indicated already, the thickness of the effective concentration boundary layer thickness will reduce or increase depending on the intensity of flow. So therefore, for a given fluid with constant thermophysical properties, the flow is very important, and the characteristics of this value will also depend on the nature of geometry that one is considering. So this tells us that at the surface mass transfer Km is not a function of concentration, but that the flux is proportional to concentration raised to the power 1. This essentially implies that we are talking of a first order process. If we have now, if we consider, for example, an unsteady state process, so therefore, what we see here that the flux can be calculated provided the mass transfer coefficient is known to us. Okay? C star will be known from the equilibrium concentration, and estimation of Cb will require that we have a knowledge of the mass transfer coefficient. So this is vice versa. So I would now say, suppose you think that I have a solid which is dissolving in a container, and this is going to be clear to you. So I can very well say that, look, A times J, the flux from the surface, so this is solid and this is fluid, and the fluid has a fixed volume, and this at say, I would say that if this is the x, let us not bother about the coordinate system, etc. here. So this is a solid, and I would say area into x is equal to 0, that is equal to the mass transfer coefficient times Ca star minus Cb. Now, what is Cb? This Cb is the bulk concentration, but this bulk concentration here is going to change as a function of time. So that will make the process as unsteady state process. Okay? Whatever is the material which is being lost by the solid, that's what is the material which is lost by the solid, is exactly equal to the material which is gained by the liquid, because this represents a closed system. There is nothing is coming in, nothing is going out. So I can say this will represent so this term essentially represents the rate at which material from the solid is going into, in terms of kg, into the fluid in terms of kg per second, and this essentially represents the amount of the material which is gained by the fluid, and they have to be equal because the material cannot escape. And V represents here the total volume of liquid contained in the system, and A represents that what is the interfacial area or the area through which the mass transfer takes place. Note that as dissolution takes place, or the solid is progressively dissolving into the liquid, the size of the solid is also changing, and as a result of which what is going to happen, this area is not going to be constant. So I could say that this could essentially represents the initial instantaneous rate of transport. If I take A to be is equal to, say, but if you assume that it is a sparingly soluble substance, so the reduction is not so much, and you are talking of only few minutes of dissolution process, so you can take that A to be is equal to pi r0, and then what happened is you can integrate this equation. So this will require one condition, and you know that at t is equal to 0, you have Cb is equal to Cbi, the initial concentration, which could be 0 also. Okay? So therefore, if you look at this equation, then we have this integral, so Cs star minus Cb, and that's going to be is equal to A by V into dt. So we have, if you integrate and apply the initial condition, then we have ln Cs star minus Cbi and ln Cs star minus Cb, and that's going to be equal to exponential, no, it is going to be A by V into T, and then we have Cs star minus Cbi, Cs star minus Cb is equal to e to the power a by v into T. This essentially tells us that C star is known from this is no Km is there, so Km into E. Yes. If you see here, so what it essentially implies that we want to find out Cb. Cbi is known in the initial condition to the problem. Cs star is also known to us because this comes from the reaction equilibrium. So A is known because which I have assumed to be pi r square with the assumptions that I have stated. V is also known. So there are two unknowns here that we have. Cb is to be calculated, and that is only possible provided Km is given to us. So given the value of Km, then we should be able to find out how concentration varies as a function of time, and that's the way the graph is being generated. Okay? May not be exactly the same graph, but because the bulk concentration is changing as a function of time, so the origin of the calculation of C versus X graph essentially relies on the measurement, on the knowledge of Km, or if you also know the value of the delta C effective concentration boundary layer, then you should be able to find out that what is the mass transfer coefficient, and then you should be able to establish how Cb varies as a function of T in accordance with. This equation will not be applicable if I, for example, say that material is, there's a material which is coming into the system and then material going out of the system, even though the volume may be remaining constant. Okay? And even though there will be no dissolved material coming into the domain, but that some dissolved material will be taken out, so there has to be some other term, you can say volumetric flow rate into C sub B. This will represent multiplied by the density, mass flow rate, kg per second, and then we have no, this should be volume flow rate, not mass flow rate. So kg per meter cube, if the concentration is kg per meter cube, and this is C sub B, note that. So this will represent then the governing equation, that mass transfer coefficient is equal to the net, what is coming into the liquid, this is this term, and what is this term? This term represents the rate at which it is going out. So, but if you are considering a closed system, in that case this term does not appear, and then this equation suffices. So therefore, it turns out that we are now concerned with the calculation of mass transfer coefficient, and now the problem boils down to exactly saying what I have discussed in the context of heat transfer, for example. So mass transfer coefficients are calculated from mass transfer correlations, and we have convective mass transfer correlations and free convective mass transfer correlation and force convective mass transfer correlation, as I have indicated earlier in the context of my lecture on heat transfer. So here in the free convection, in the case of heat transfer, it is the temperature gradient which was causing the density differential and driving the flow. But in the case of mass transfer problem, it is the concentration difference, because with concentration the density is going to change, and it's the concentration differential that creates the density difference, and that density difference in turns drives the flow itself. So in the context of heat transfer, it is a thermal free convection phenomena, and in this particular case we will say it is a solutal free convection phenomena, and there may be systems where both thermal free convection as well as solutal free convection can be persistent together or existing together, and we will say such phenomena to be a combined thermosolutal, or the free convection current generated there should be a combined, the result of a combined thermal and solutal free convection. So if you remember that force convection heat transfer correlations were Nusselt's number, Reynolds number, and Prandtl number, and in this particular case, so the heat transfer correlation was this. I can go rather quickly here, okay, because we are exposed to these subjects and there is one-to-one mapping. So forced convective heat transfer was Nusselt's number, a function of Reynolds number and Prandtl number, and free convection forced convection heat transfer. Let me just convective heat transfer, and then free convective heat transfer. We have Nusselt's number is equal to function of Grashoff's number and that Prandtl number. I have also shown that how the Grashoff's number can be translated to an equivalent velocity scale, and this Grashoff's number generates a velocity field which is directly related with the thermal gradient which is present in the system. This is the ratio of the momentum diffusivity to thermal diffusivity, and this is the Reynolds number, and this is the Nusselt's number, where we use, as I have indicated, what is known as the thermal conductivity of the liquid and not the solid, if you remember correctly. So now, for example, the equivalent of Nusselt's number in mass transfer is the Sherwood's number, and this is defined as heat transfer coefficient into characteristic length divided by the fluid thermal conductivity. So therefore, the Sherwood's number is defined exactly the same way, which is mass transfer coefficient into characteristic length divided by the diffusion coefficient. That means this is the diffusivity of the diffusing species through the liquid. That's what is this diffusion coefficient. And this is going to be a function of Reynolds number, which is defined exactly the same way, and then the corresponding to Prandtl number, we have Schmidt number. And this Prandtl number is nu by alpha. On the other hand, this Schmidt number is nu by d. This X shows the, embodies the relevant properties which causes. So this is the convection effect, this is the diffusion effect, and this is the net result. That's why we kept the effect of convection and diffusion on the mass transfer, and this becomes an independent variable, and these are the independent variables. Similarly, for free convective heat transfer, we have used Grashoff's number, and this also I said we can represent as GR sub T, thermal Grashoff's number, and then we have Nusselt's number as a function of Grashoff's number, okay? And this you can say as a mass transfer Grashoff's number, and instead of Prandtl number, we can write Schmidt number. And here, the Grashoff's number is defined as, I would say, rho square, then L cube, G delta rho by, is a modulus of delta rho, and then rho square by A square. And this delta rho value is related to the concentration differential. In thermal problems, the delta rho value is related to the heat transfer problems, and that's what is the Grashoff's number. We have we'll study the similarities between the heat and mass transfer when we discuss about the Reynolds analogy a little late. Same type of correlation. For example, in the heat transfer, we have seen from a spherical geometry, I have demonstrated that for when we have pure diffusion case, the Nusselt's number becomes is equal to 2, and I have also demonstrated that the Sherwood's number also become equal to 2. Now, for forced convective heat transfer, I have shown that Nusselt's number is equal to, diameter based Nusselt's number is equal to 2 plus 0.6 diameter based Reynolds number raised to the power half into Prandtl number raised to the power 1 by 3. And this correlation, if you remember, I said the Range-Marshall correlation, okay? And this is the convective component, contribution of convection over diffusion in heat transfer. And we have 1-to-1 parallel, we say Sherwood's number diameter is equal to 2 plus 0.6 Reynolds number diameter Schmidt number. This is the equivalent correlation applicable. Similarly, if you say mass transfer from a flat plate, okay? If you have a flat plate here, and then you have fluid is flowing, U infinity and C bulk. So the flat plate correlation comes out to be Sherwood's number plate length, and this I call as plate average Sherwood's number, where the characteristic length is the plate length, and this is equal to 0.33 into Reynolds raised to the power half and Schmidt raised to the power 1 by 3. This comes out, so we can have a local number also. Many times we will come across, and this is actually 6, I think, and this is a local force convective mass transfer correlation. So looking at the value, the moment you see x, you can understand that it's a local correlation. If you look at, see that the suffix of Sherwood's represents capital L, so you can say it is a average, because once you have a concentration versus, everywhere the slope of the line is going to be changing. The slope of the line here is not same as the slope of the what line? Concentration versus distance line. If I draw the concentration from here to here, the slope is going to be, slope at x is equal to y is equal to 0 is going to be different here, different here, different here, different here, different here. So that essentially indicates that the effective concentration boundary layer evaluated at this point will not be same as this, not be same as this, not be same as this. So therefore there is a variation of effective concentration boundary layer or mass transfer coefficient across the plate length. And so this gives us the local value of the mass transfer coefficient, and if you do integrate that local correlation over the length of the plate, which is capital L, then we should find out. So this I have extensively discussed, the governing equations of fluid flow, the equations of continuity, the equations of motions along the x and the y direction, two-dimensional flat boundary layer over a flat plate, and then also thermal balance equation. So the thermal balance as well as the concentration balance or mass balance equations will look almost similar or practically similar. So therefore 1-to-1 correspondence exists, and the similar correlations are also available. So for every geometry, for plate, for sphere, for cylinder, we have force convective and field convective correlations available in the literature. So we have to understand that which geometry, which condition. For example, these correlations are valid for laminar flow and may not be extendable in a straightforward fashion to turbulent flows. Okay? So therefore, once we understand the basic nature of the problem, we can refer to the correlations, and then these correlations allow us to calculate the characteristic mass transfer coefficient on the basis of the variables which are given on the right hand side. So therefore, once the mass transfer coefficient is calculated, in that case we can calculate the flux by taking the concentration differential, or at least we can consider a mass balance equation like whatever I have shown here. If you remember, K multiplied by the concentration difference is equal to V into rate of change of bulk concentration. So you can write a mass balance equation. So therefore, these correlations together with an appropriate mass balance equation will provide us the framework for calculating how the concentration at different point in the system is changing as a function of time. Now, if you say, sir, I want to find out how the concentration is changing at different locations, then this spectroscopic approach is not going to work. In that case, you have to solve the exact Navier-Stokes equation, you have to solve the convective heat and convective mass transfer equation, and that convective mass transfer equation in this case, if you consider steady or unsteady, this will look like, let me just erase this and then I will write it. This approach works when there is good amount of turbulence in the system. So you say, sir, I am not interested that, what is the difference in concentration between the 2 points or several points, because the intensity of fluid motion is very large here. So the mixing is very rapid. There is basically no concentration difference in the bulk of the liquid. In that case, whatever I have discussed so far is adequate. But if you insist that no, I want to find out that what is the concentration distribution in the entire domain of interest, in that case, you have to write the governing equation. For example, if I write it in Cartesian coordinate, okay, so then we can say that this is c into u. U represents the x directional velocity. Then we have c into v, and then we have if we assume that there is no reaction and no mass generation in the system, dc. And this equation you have to solve in the context of a flat plate boundary layer, and then only you will be able to find out that how does, because this equation tells you that how concentration varies as a function of time distance. Earlier I told you that I was taking a global approach or an average approach, and I was calculating that at what rate the concentration, bulk concentration is changing. There was no xy dependence on concentration, but in this case, since we want to find out how x and y is to be, c is varies for different x and y, we have to solve this equation. There is no shortcut. Okay, and to solve this equation, this is an equation which is applicable for two-dimensional Cartesian coordinate system and for laminar flow. It is not time averaged equation, as I have said earlier. Okay, and therefore it will require that in addition to the diffusion coefficient, okay, this will demand that you can solve this equation provided the distribution of velocity is given. Then only this equation becomes one equation, one unknown, given the velocities, and if you have the correct initial and boundary conditions, you should be able to solve, and then by solving you should be able to extract the information on c, t, x and v. This is a subject we don't want to dwell on much beyond this particular point, because this requires simulation of the or calculation of the flow field. Then following that you have to calculate the concentration field, and because of multidimensionality, because of sometimes non-linearity, particularly in the flow equations, we cannot solve it the way we have solved many of the problems in the class. So therefore we don't want to discuss this, but there are approaches which is available. Even if it is turbulent flow, you have approaches available, so you can formulate the equations, you can go to a computer, write computer programs, solve the equations and work out the implications of the model, and find out that how concentration not only changes as a function of time, but also spatial distribution of concentration in the domain of interest. Now, this correlation, for example, as I have indicated in the context of a cylinder, that Sherwood's number, okay, and cylinder is based on the diameter of the cylinder, and this is something like I think 0.3 into Reynolds number diameter, typically half into Schmidt number. So this correlation for a cylindrical geometry in laminar flow. Because when you go to, if the flow is turbulent, sometimes what happens is the boundary layer, the turbulence from the bulk can penetrate into the velocity boundary layer, and then what happens is the characteristics of the concentration boundary layer, particularly if it is thicker in comparison to the velocity boundary layer, what happens, the boundary layer, concentration boundary layer itself can turn into turbulence, and then the turbulence can aid into mass transfer. So while such correlations, which is valid for cylindrical geometry and applicable to laminar flows, are not applicable in many systems, industrial systems, where turbulence penetrates inside the boundary layer, or the boundary layer has essentially turned into turbulence. And in that case, what happens is the correlations get modified, and there are other dimensionless parameters like the intensity of turbulence, which is embedded into such correlations, which are basically empirically determined. That means you carry out certain experiments, and then you study the fitting, and then you say that if you introduce the turbulence parameter like a turbulence intensity, which is the ratio of fluctuating component by the mean component of the motion. So that's what is the intensity of turbulence, and these equations can be rendered applicable to turbulent flows by introducing the effect of turbulence into the correlations, and one such parameter is the intensity of turbulence. So just like the way some people also say that, look, if you have a nominal Reynolds number which is based on the mean velocity component, then you can also have a Reynolds number based on the fluctuating velocity component, where u prime essentially indicates the fluctuating component, and this we can say as a turbulent Reynolds number. Okay? And basically what happens is turbulence Reynolds number, if we represent as T, is equal to nominal Reynolds number multiplied by the intensity of turbulence. That's what it is. Because this u bar here in I is going to exactly cancel with the u bar in this particular expression, because u bar is going to be in Reynolds number sitting in the numerator, and u bar is going to be sitting in the denominator, so they will cancel out and the resultant expression will be exactly same as this. So the effect of we have many correlations which are available to us for different geometries, for laminar flows, for turbulent flows, and this we can we can access this, and then on the basis of such, by substituting proper values, we should be able to calculate the mass transfer coefficient. And those cases where we want to only know how the concentration is changing as a function of time, or how the rate of dissolution is progressing as a function of time, we should be able to take the global approach that I have mentioned earlier. That means write the first order equation, and deduce the first mass transfer coefficient from a correlation, then set up a mass balance equation, and it's all done. You should be able to predict the rate of change of concentration in the bulk of the liquid. The last point here I want to talk today is the the analogy between heat and mass transfer. So this, you have seen that the correlations that I have written here, essentially they are more or less similar. Okay, the heat transfer correlation, the Reynolds number, Prandtl number dependence, and here we see that it is a Reynolds number and Schmidt number dependence in the case of forced convection. So there is one-to-one similarity, and this we have. If you go back now to my lecture, first lecture, and where I wrote that we have the Newton's law of viscosity, or which also can be represented in terms of kinematic viscosity into, I am not labeling the axis etc., because I have done it several times. Okay, so you can imagine that Vx represents, if Vx represents the x directional velocity, and we are talking of the gradient along the y direction, that's what it implies. And these notations also, Yx essentially, one is the normal direction and one is the x momentum along the y direction. And this I have also shown that this is the flux of momentum. Similarly, the flux, heat transfer flux, I have shown that this is equal to minus k. So we can also say that this is basically the flux is, if you consider it to be rho Cp to be constant, and this is nothing but my alpha into the same thing. And in mass transfer, so this is a heat transfer. This is the Q is the flux. So I should say that this is this has to become, and then the mass flux, which is represented by J, and that is, we know that this is in the case of pure diffusion. So to be consistent, I will write here and we see that the diffusion, and that's why they're all the phenomena, flux, momentum flux, heat flux, mass flux, they are all related to the gradients of the principal variable here, the variable of interest. And it is because of that, the gradient, I said that in the beginning, that gradient is a characteristics of diffusion process. The gradient of velocity characterizes momentum flux, the gradient of temperature characterizes heat flux, the gradient of concentration characterizes the mass flux. So there is lot of similarity between the heat and the mass transfer itself. And we have seen that the correlations really some correlations I have shown here. So, there is one-to-one similarity between heat and mass transfer. So, for many situations this has been worked out, and I am not going to the details of it. So, basically it is said that there is a J factor for heat transfer and mass transfer. The J of heat transfer basically is Nusselt's number divided by Reynolds number into Prandtl number into Prandtl raised to the power 2 by 3, and this is equal to J of mass transfer, which is equal to also, instead of Nusselt's we will get Sherwood's, and then we have Reynolds. The derivation I am not going to show you, Reynolds and Smith, and then we have Schmidt number raised to the power 2 by 3, and that is equal to f by 2. And what is this? This we know, dimensionless numbers. This is the J, we call it a J factor, okay, in the context of the Reynolds analogy, and F represents the friction factor. And the friction factor, you may have heard it, okay, when you have studied your fluid dynamics course in undergraduate, and we can say that this is defined as F into A into K. The definition of F is given here. So, what is Fk? Fk is the kinetic force. What is K? K is the kinetic energy per unit volume, and A is the area. If you compare the values, then F is actually a dimensionless parameter. For flat plate geometry, this correlation really comes out to be, I think, 0.03 divided by Reynolds number raised to the power. These correlations are not universal. So, for the moment I have assigned a value here, it becomes specific to a flat plate geometry, and this allows us that, if you can do a heat transfer experiment, for example, determine the Nusselt's number, this will allow us to determine that what is the corresponding Sherwood's number. That is the beauty of the whole thing. I do not have to study separately the mass transfer phenomena. By studying the heat transfer, I can interpret about the mass transfer phenomena, and also I can have a good estimate of the corresponding friction factor, which can follow in this particular case. So, for a given Reynolds number, the friction factor can be easily calculated, which is of interest in many of the problems. So, therefore, the similarity between heat and mass transfer, which has been enunciated so long, can, this is, I think, Reynolds, this is called analogy. Between heat and mass transfer, and therefore, the beauty of it is that I have written two what you call correlations, that's the Range-Marshall correlation for mass transfer, Range-Marshall correlation for heat transfer, and you have seen that the correlations have forms which are exactly identical. So, what does this indicate? That the analogy tells us that for identical scenarios there can be one-to-one replication between the various dimensionless groups. So, one need not have to carry out a fresh additional mass transfer experiment. If one has done heat transfer experiment, he can find out the corresponding scenario for mass transfer and vice versa. So, we will continue with our last topic, that is the mass transfer between two fluids, in the next lecture.